For 10,000 years, human civilization operated within boundaries that never moved. Power came from muscle, from wind, from water falling downhill. But in the second half of the 18th century, something unprecedented began to unfold in the coal-rich, rain-soaked Midlands of Great Britain. Humans discovered how to pull concentrated energy out of the ground, burn it, and convert that heat into mechanical motion on a scale the ancient world could never have conceived. We call it the Industrial Revolution. It represented the single greatest rupture in the history of human productive capacity. It was the moment civilization stopped running on sunlight and started running on stored carbon. To understand why the revolution started where it did and when it did, we must examine the specific conditions that made Great Britain uniquely positioned to ignite this transformation. 5 structural advantages converged in Britain during the mid-18th century that existed nowhere else in combination. First was crop yields. Farms across Britain had already adopted iron ploughs and Jethro Tull's seed drill, generating more food per acre with fewer workers. This generated a surplus rural population. Hundreds of thousands of people freed from the land and searching for wages elsewhere. Second was political and legal stability. Britain's constitutional framework protected private property and allowed entrepreneurs to form joint stock companies, raise capital, and defend patents in court. Third was geography. As an island nation threaded with navigable rivers and lined with natural harbours, Britain possessed an internal transport network that kept the cost of moving goods low. Fourth was the intellectual inheritance of the 17th century scientific revolution, which had created a culture of empirical inquiry and practical experimentation. And fifth, perhaps most decisive of all, was the economic equation between labour and energy. In Britain, wages were high and coal was extraordinarily cheap. It was cheaper to build a machine than to hire a man. Before the factories, the dominant system of textile production was what economists call the putting out system. Merchants would distribute raw wool or raw cotton to families scattered across villages in Lancashire and Yorkshire. Women would spin the fibre into yarn inside their own homes. Men would operate hand looms to transform that yarn into cloth. It was slow, dispersed, and intimate. It was a domestic life, organised around the rhythm of the household. But the demand for cloth was growing at a rate that this cottage system could not satisfy. Britain had acquired a vast global empire and the appetite for textiles that came with it. The pressure was building. The specific catalyst was cotton. Britain could not initially compete with the hand-woven cotton cloth arriving from India. Indian labour was roughly 5 times cheaper, and the quality of Indian weaving was unmatched. The British government attempted to shield domestic producers by passing the Calico Acts, which restricted the import and sale of Indian cotton cloth. These protectionist measures did not stop demand. They redirected it. British entrepreneurs faced a clear challenge: produce cotton cloth faster and more cheaply than any other nation on earth, or lose the market entirely. Necessity, as it has always done, drove invention. The first decisive mechanical breakthrough came in 1733 when John Kay invented the flying shuttle. This deceptively simple device allowed a weaver to throw the shuttle across the loom mechanically rather than passing it by hand, doubling the speed at which cloth could be woven. The immediate result was a crisis. Weavers could now consume yarn far faster than spinners could produce it. A single weaver required the output of roughly 8 spinners just to keep the loom running continuously. This bottleneck choked production for decades. It was a structural imbalance that demanded a structural solution. The solution arrived in stages. James Hargreaves introduced the spinning jenny around 1764, a wooden-framed machine that allowed a single operator to spin multiple threads simultaneously. It was compact enough to fit inside a cottage. Then came Richard Arkwright with the water frame, a spinning machine of a fundamentally different character. It was too large and too powerful to operate inside any home. It required the force of a river current to drive it. Arkwright built the first purpose-built cotton mill at Cromford in Derbyshire in 1771, and in doing so established a new principle. Production was now an industrial process, conducted in a dedicated structure, not a domestic one. Shortly afterward, Samuel Crompton merged the mechanical principles of both technologies into the spinning mule, which produced thread of a fineness and tensile strength that no human hand could replicate. The transformation of cotton was complete. The statistical result of these inventions was staggering. In 1750, Britain imported approximately 2.5 million pounds of raw cotton annually. By 1850, that figure had risen to 588 million pounds. Manchester, which had been a modest market town of fewer than 10,000 inhabitants in the early 18th century, became known to the world as Cottonopolis. It was a city of over 900 factories, its skyline permanently obscured by coal smoke, its streets vibrating with the mechanical hum of tens of thousands of spindles running without pause. The cost of cotton cloth collapsed. What had once been a luxury accessible only to the prosperous became affordable to nearly everyone. While the Textile Revolution was remaking the surface of British commerce, a second and equally profound revolution was taking place underground. As coal mines were driven deeper into the earth to satisfy the growing demand for fuel, they encountered an ancient enemy. Water. Groundwater seeped into the deepening shafts and flooded them. The horse-powered pumps in use at the time were inadequate for the volumes involved. The coal industry faced a physical ceiling imposed by geology. The response was the steam engine. In 1712, Thomas Newcomen installed the first commercially viable atmospheric steam engine at a mine in Dudley. It worked by creating a partial vacuum, allowing atmospheric pressure to push a piston downward and drive a pump. It was enormously inefficient, but it solved the flooding problem well enough to allow mines to go considerably deeper. The engine that changed everything, however, came from the workshop of a Scottish instrument maker named James Watt. Working at the University of Glasgow in 1765, Watt identified the core inefficiency of the Newcomen design. The cylinder had to be alternately heated and cooled during every stroke, and the energy required to reheat a cold cylinder was enormous waste. Watt's insight was to add a separate condenser chamber, so that the main cylinder could remain continuously hot while condensation occurred elsewhere. Working in commercial partnership with the Birmingham manufacturer Matthew Boulton, Watt developed and patented this improved design through the 1770s. The efficiency gains were transformative. Watt engines consumed roughly 3 times less coal than equivalent Newcomen engines for the same mechanical output. By the early 1780s, Watt had developed a rotative version of his engine, one that converted the back and forth motion of the piston into continuous circular rotation. A factory could now be built anywhere, powered entirely by burning coal. Steam was applied to virtually every industrial process. It drove the bellows of iron blast furnaces, hammered metal in forge works, and ran the spinning frames of textile mills. The productive capacity of Britain multiplied year by year as steam engines were installed across the manufacturing districts. The horsepower available to British industry grew at a rate that had no historical precedent. But steam did more than replace human and animal labour. It unlocked the iron industry in a way that reshaped the physical world. Iron had been smelted for millennia, but always using charcoal derived from wood. The supply of suitable timber was finite and already declining by the 17th century. The breakthrough came from the Derby family of Coalbrookdale, who demonstrated through the early 18th century that coke, a refined form of coal produced by driving off impurities, could fuel a blast furnace as effectively as charcoal. This removed the ceiling on iron production entirely. Blast furnaces grew larger. Output expanded dramatically. As pig iron became cheaper and more abundant, it transitioned from a specialized engineering material to a primary structural one. The iron bridge spanning the River Severn at Coalbrookdale, completed in 1779, was the first cast iron bridge in the world. It announced to Eve, Rye engineer, entrepreneur, and government on the continent that a new structural material had arrived. New refining techniques, particularly the puddling process developed by Henry Cort in the 1780s, allowed wrought iron of superior quality to be produced in quantities and at costs that made it commercially viable for construction on a massive scale. Their labour built the infrastructure of a new world. The infrastructure of distribution had to expand to carry what industry was producing. The old road network, built on medieval foundations, could not move bulk materials efficiently. Coal, iron, and raw cotton required something better. The first answer was canals. The Bridgewater Canal, completed in 1761 to carry coal from the Duke of Bridgewater's mines at Worsley into Manchester, demonstrated that water transport could reduce the cost of coal delivery by more than half almost immediately. The commercial success of this single project set off a period of intense canal construction across Britain throughout the 1770s and 1780s. By 1800, Britain had approximately 3,000 miles of navigable canals. The canal system bound the manufacturing districts together into a coherent economic network. But the canals were eclipsed within decades by an invention of far greater consequence. The railway was made possible by the convergence of cheap wrought iron for rails, precision rolling mills to shape them to a consistent profile, and the high-pressure steam engine developed by Richard Trevithick in the early 1800s. Trevithick built the first steam locomotive to haul a load along iron rails in 1804. The opening of the Stockton and Darlington Railway in 1825 and the Liverpool and Manchester Railway in 1830 announced the railway age to the world. The Liverpool and Manchester line was a technological and commercial sensation. It linked a major inland manufacturing centre with a global port. Goods that had previously taken days to move by road or canal could now be transported in hours. The human consequences of industrialization fell most heavily on those who built and operated the new economy. The cities of northern England grew faster than any urban centre in recorded history. Manchester's population expanded from roughly 10,000 in 1717 to over 300,000 by 1850. This growth was entirely unplanned. There were no building codes, no sanitary regulations, no civic infrastructure adequate to receive hundreds of thousands of people arriving from the countryside over the course of a few decades. Workers were packed into back-to-back terraced housing, sometimes with entire families occupying a single room. Cellar dwellings were common. There were no sewage systems. Waste accumulated in the streets and drained into the rivers. Rivers ran with chemical effluent. Drinking water was contaminated. Cholera and typhoid were endemic. In the worst districts of Manchester during the 1840s, average life expectancy at birth had fallen below 30 years. Inside the factories, a new form of human organisation emerged. The factory system did not merely change where people worked. It changed the fundamental relationship between a worker and time. In the pre-industrial world, agricultural labour followed the natural rhythms of daylight and season. In the factory, work followed the machine. Machines ran continuously, and humans were required to match their pace. Shifts of 12 to 14 hours were standard across the textile mills of Lancashire and the metal works of Birmingham. 6 days a week, for wages that left almost no margin. The discipline enforced was rigid. Workers who arrived late were fined. Those who fell asleep at their frames were fined or dismissed. The factory was a new kind of institution with its own internal logic. A particularly grave dimension of this new system was the employment of children. Child labour was not invented by the Industrial Revolution, but the factory concentrated it, systematized it, and made it more visible and more damaging than anything that had come before. Children as young as 6 or 7 were employed in the cotton mills, often as scavengers who crawled beneath moving machinery to retrieve fallen threads and clean accumulated lint. They worked in conditions of continuous noise, dust, and mechanical danger. The Factory Act of 1833 was the first major legislative response, prohibiting the employment of children under 9 in textile mills and limiting the working hours of children under 13 to 8 hours per day. It was an inadequate measure that nonetheless established the principle that the state had authority to regulate conditions inside a private factory. Not everyone accepted the transformation without resistance. Skilled handworkers whose expertise had accumulated over a lifetime found themselves undercut by machines that could replicate their output at a fraction of the cost. The Luddite movement of 1811 to 1816 was the organised expression of this desperation. Groups of framework knitters and weavers across the East Midlands and Yorkshire broke into workshops and destroyed the machinery they held responsible for their displacement. The government responded with military force and legislation, making machine breaking a capital offence. 17 men were executed following the trials at York in 1813. The machines stayed. The handweavers did not recover. From this period of industrial conflict, the trade union movement began to take rent shape. Workers discovered that collective action could accomplish what individual protest could not. Despite legislation that initially criminalized combination, unions gradually won legal recognition and the right to bargain over wages and conditions. The revolution also created a new social architecture. Alongside the industrial working class, the factory system generated a substantial and growing middle class. Mill managers, clerks, accountants, engineers, and commercial agents occupied a stratum of society that had not previously existed in significant numbers. These households furnished their homes with manufactured consumer goods, many of them products of the very industries that employed them. Wedgwood pottery, cotton curtains, refined sugar, and printed calico were accessible to middle-class households in ways they had never been to any previous generation. A consumer economy was forming around the productive capacity of the factories. By the middle decades of the 19th century, the industrial techniques that had originated in Britain were spreading across the Atlantic and across the continent of Europe. Belgium was the first nation to follow, its coal-bearing region of Wallonia providing a resource base that made rapid industrialization viable. Transplanted British engineers built integrated manufacturing works in the Liège district that were producing steam engines and machinery by the 1820s. France industrialized more gradually, building on existing craft traditions rather than displacing them entirely. The German states presented a different pattern. Politically fragmented and lacking a unified internal market, Germany was initially slow to concentrate industrial capital. The construction of the railway network in the 1840s and 1850s changed the calculation entirely. By the time of German unification in 1871, Germany was not merely catching up with Britain. It was beginning to surpass it in key sectors of chemical production and steel manufacture. Across the Atlantic, the United States absorbed the essential knowledge of British industrialism and modified it in ways that suited a country with a different economic profile. American wages were even higher than British ones, and the pressure to substitute machinery for labor was correspondingly greater. The solution developed in New England armories and clock factories was the system of interchangeable parts. Rather than producing each component individually by a skilled craftsman to a custom fit, American manufacturers developed machine tools capable of cutting metal parts to tolerances precise enough that any component would fit any assembly. This concept applied first to firearms and then to sewing machines, agricultural equipment, and eventually to every manufactured product, laid the foundation for mass production on a scale that the early British mills had never anticipated.